Good afternoon, everybody. Welcome to this episode of Authors at Google. I'm Dan Russell, and I'm the host for our guest today, Jeff Johnson. And I know Jeff because back in the mid-'80s, we were both at an institution known as Xerox. I was at PARC, and Jeff was at Office Information Systems. That means he got to work on the Xerox Star, which if you go down to the Computer History Museum, you can find, right? It was a fantastic, groundbreaking system that commercialized a lot of the ideas that later showed up in things like, the Macintosh and other kinds of systems. You've actually used, may or may not know it, you've actually used a lot of the work that Jeff has done over the years. He's also not just a user experience person, but he programs in Java, Mesa. Does anybody remember Mesa? C++, even things like APL. So he's a remarkable guy who's probably best known for his Bloopers series of books, and you can come and check out some of them up here later. The one I first saw was GUI Bloopers, but then there were Web Bloopers and Web Bloopers 2.0, which are sort of catalogs of all the mistakes that we make and we should learn from. So these are really interesting books if you're at all interested in user experience design. So Jeff's talk is a part of the growing user experience education effort that's being led by the infrastructure team. And we're going to be having more tech talks in this series, so please stay tuned. If you like this one, we're going to have more, and you'll enjoy the participation in that. Also notice that we're coordinating, well, Cindy, who's sitting back over there with her hand up, is coordinating a workshop and tutorial here, well, somewhere here at Google, on February 7th, right? February 7th, where Jeff and Austin Henderson will be talking about returning the notion of conceptual design models. That will be open for registration on gLearn, I guess, in a week or so? Real soon now. And there's space for 50 Googlers, okay? So sign up soon if you want it like that. Jeff's book will be available in the back for $15, cash or credit card. So if you like his talk, you're gonna love his book. So please join me in welcoming Jeff Johnson to talk to us about how to design with minds in mind. Jeff.
Thank you. So thanks to Cindy Yepes and Robin Jeffries for arranging this talk, and to Dan for hosting it. Okay, so how many of you design user interfaces? Good number, good. Well, those of you who do that, how many of you have ever looked at or seen user interface design guidelines like the ones I'm displaying now? These were developed by and published by Ben Shneiderman in 1987, and all subsequent issues of his book up to now, they remain much more or less the same. How many of you have seen guidelines like these when you're designing user interfaces? Okay, so now we'll look at some similar guidelines that were published by Nielsen and Molich. They were intending these to be used for website design and website evaluation. Now, I'm not going to go through the guidelines in detail because that's not the subject of this talk, but I will point out that there's similarity between these guidelines and those that have been put forward by Ben Shneiderman. So the question is, did Nielsen and Molich plagiarize the earlier guidelines by Ben Shneiderman? And then subsequently, did Debbie Stone and her colleagues in the book that they published in 2005 has a similar set of guidelines? Did they plagiarize? What was the reason that these guidelines were much the same in these different publications? Well, I'm going to argue that the reason is not plagiarism. The reason is that guidelines, user interface guidelines, are based on us. They're based on how we work. That's where those guidelines come from. Now, I used to be in the guidelines business, or actually anti-guidelines. So when I wrote GUI Bloopers and its sequels, I was sort of in the don't do this instead. But I didn't really explain it in those books why. And I found that user interface designers typically are not satisfied with just being told, thou shalt, or even thou shalt not. They like to know why thou shalt. Why shalt thou? And so the other problem is that it's difficult to follow those guidelines if you're a designer. Let's go back and look at some of those guidelines for a second. First step to goal should be clear. What does that mean? That's pretty vague. First step is fairly clear, but what does it mean for the first step should be clear? What is clear? What makes something clear? When is something not clear? So the point is that guidelines are not rote recipes that you can just follow without any background knowledge. Applying user interface guidelines effectively requires understanding their scientific basis, understanding where the rules came from, so that you can balance the trade-offs that occur when there are competing rules. You know, somebody says to you, make it fast, make it high res. Well, maybe you can't do both of those things, so you have to choose, or you have to find some kind of trade-off. It helps to understand where the rules came from in order to be able to apply them. So I wrote this book that was about that. That's basically about how the human perceptual cognitive processor works, and, or I should say processors, I'll get to that later, how it works, and where do these design rules come from? That's what the book Designing with the Mind in Mind is about. Books have chapters, so each of the chapters, some of the chapters deal with perception. I'm listing here on this slide those perception chapters, and then there are some chapters on cognition. I'm not going to talk about everything that's in the book. It takes about 2 days to give a tutorial that covers the entire book, and we have an hour. So I'm just going to cover a few of the facts about human perception and cognition in this talk. Show you some examples. So the first one is that we perceive what we expect. What you are perceiving right now is not what is really here. What you're perceiving right now is biased heavily by many things. The main things that I'm going to talk about right now that bias your perception are the past, the present, and the future. Okay? The past is your experience. The present is the current context, everything else that's going on right now in this situation. And the future is your goals. What are you planning to do? What are you trying to do? All of those things heavily bias your perception. Your perception is almost in no way reflective of what is actually out there in the world. I'll put it that strongly. So I'm going to show you some examples. How many of you are familiar with the art of Jackson Pollock? So here's Jackson Pollock. He's landed a great gig. He gets money for throwing paint onto canvases, splattering paint on canvases. What a great gig. I wish I could get a gig like that. Okay, so I'm going to show you a Jackson Pollock image, Jackson Pollock painting. Did everyone see the splatter painting? Okay, so now I'm going to show you something else. I'm going to show you a dog sniffing the ground next to a tree. It's a Dalmatian. Does everyone see the Dalmatian? So there's the dog. There's the tree. He's sniffing the ground. His tail's in the air. Hind feet, front feet. Okay? So this is actually a famous image by a guy named R.C. James. I could basically tell you what you were going to see by showing you pictures of Jackson Pollock painting and things like that, and then telling you you were going to see a splatter painting. So basically, the past influenced your perception. Now I've told you it was a Dalmatian, and then I showed it to you. And how many of you see the Dalmatian, by the way? It's about everyone. And now the interesting thing is, if you ever see this picture again, you'll never not see the Dalmatian, ever again. So how does this what does this have to do with computer system design? Well, let's assume that we have a multi-page dialog box, otherwise known as a wizard. So it's a multi-step dialog box. It doesn't matter what's on the pages. So if you watch someone using a wizard in a usability test, what you'll see is fairly predictable. So basically, they read what's on page 1, whatever it is. They fill out whatever fields are there, and they click Next. And it goes to page 2. And so then they read whatever's on page 2, and they fill out any fields, and they go to click Next, and it goes to page 3. And then they fill it out, and then they go to page 4, and then they click the back button. And it goes back to page 3. And they said, why did it do that? I clicked Next. And you say, no, I was watching you. You clicked back. And they say, no, I didn't. I clicked Next. And you say, no, I was paying attention to what you were doing, and you clicked the back button. And then you take them to page 4. And they, oh, the back button is in the opposite place than it was on all the other buttons. Of course, they didn't notice that because they weren't paying attention to the position of the buttons. They were paying attention to their task of whatever it was, buying an airline ticket, reserving a hotel room, whatever it was. So their perception was based on their past experience, not only with this dialog box, pages 1, 2, and 3, but with all previous wizards that they'd used before. Okay? So that biased their perception. Now let's talk about current context biasing perception. Here we have two symbols. They're identical. They're the same symbol. But depending on what context I put them in, your eyes will perceive them, or more accurately, your brain will perceive them as an H that's kind of crooked or an A that's open at the top, automatically. Or let's move away from the domain of letters to the domain of graphics. So we have a line here. This is called the Muller-Lyer illusion. So we can take that line and duplicate it. So now there are two of them, exactly the same line. And then we put these on them. And now, even though you know that it's the same line, your eye sees the top one as longer than the bottom one. And you can't actually stop yourself from seeing it that way. So this is context affecting perception. Now, here's the interesting thing, is that the brain is multimodal. It has many senses. As you know, you have many senses. And the context can be cross-modal. The context influence, the biasing of sensory input by, the biasing of perception by sensory input can be from other sensory modalities. So there's a famous effect called the McGurk effect, which I'm just not going to show you, which is that based on what you're looking at. By the way, let me ask you this question. How many of you can lip read? Well, in fact, you all can lip read, because, as you're about to see. Okay? Now, I want you to listen to what this man is saying, and I have to give credit to some unidentified blogger on YouTube who put this video on YouTube. It's probably the best demonstration of this that I've seen, and it's unidentified, so I don't know who to credit. But I want you to watch this video.
Ba 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 ba.
He's saying the same sound.
Ba 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 ba.
You hear a different sound depending on which guy you look at.
Ba 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 ba.
That's an example of your hearing being biased by what you're seeing. You can actually all lip read, and you didn't know it. And as I said earlier, the future also biases your perception, your goals, what you're intending to do. You tend not, people, especially adults, tend not to notice things that are unrelated to their goals. Our mind is designed to notice the things that are related to what we're trying to do, okay? So I'm going to show you the contents of a toolbox, and I want you to tell me if there are scissors in the toolbox, okay? Were there scissors? Okay. Was there a wrench? Ah, it's okay. Some people saw the wrench. So there is a game you can play in your house if you have guests. I'll describe it quickly, which is if you're sitting in your living room and your guests are with you in the living room, you can send them into the kitchen, and probably in your kitchen somewhere you have a drawer that has random kitchen stuff in it. I know I do. And you can tell them, go to that drawer, it's the third one down from the left next to the refrigerator, and get me the turkey baster and bring it back. And then when they come back, you say, was there a meat thermometer in the drawer? And they will have no idea. Most adults will have no idea. Now, a 6-year-old actually will probably have a pretty good idea of all the other stuff in the drawer if you can get them to come back in the first place because of all the cool stuff that was in the drawer. But that's because their brain isn't quite as goal-directed as the adults is. So in terms of website design, for example, if I put you on the home page of the University of Canterbury's website, and I say, I want you to find me somewhere in this website a map of the campus that shows the computer science department and where it is, your behavior at that point is very predictable. What will happen is your eyes will start moving randomly. Oops. Your eyes will start moving randomly around the screen in very quickly. Your eyes move 10 times a second, tenths of a second per saccadic eye movement. Your eyes are moving very quickly all the time in almost random motion. But because I gave you the goal of looking for a map of the computer science department on this website, your eyes will spend a lot of time over these places where it says departments, the word departments, the campus map, and maybe also your eyes will zero in on the search box because you're starting to think about maybe typing something in there and looking for search box. But you will probably exit the page without ever noticing that you've been randomly selected to win $100 because nobody asked you to look for that. Now I'm going to talk about color vision. The human color vision system is very unlike a camera. A digital camera is depicted by this, this graph on the right. So on the right, essentially what we have is the spectrum across the bottom of the graph. And what we have is, in a camera, we have on the plate at the back of the camera, we have a bunch of photosensitive units, cells, you can call them. And a pixel is made up of 3 cells, one that you would call a red sensor, one you call a green sensor, one you call a blue sensor. The red sensors are sensitive to light in a certain range. The green sensors are sensitive to light in a certain range, and the blue have a certain range. And notice those ranges they overlap a little bit, and the amplitudes or the maximum sensitivity of the 3 kinds of sensors is approximately the same. It's designed that way. That isn't how the human eye works at all in terms of color perception. The human eyes has, well, let me ask you this question. How many of you remember from high school or college that we have rods and cones, and the cones are for black and white, I'm sorry, the cones are for our color perception, and the rods are for black and white and sort of brightness. How many of you remember that? Well, you can sort of forget it because it's only partly true. The rods really, we don't use them very much in modern industrial society. They were designed for use when we lived mostly in the dark. And let me ask you this. how long ago was it that people lived their lives mostly in the dark unless it was daytime? About 100 years ago. It was only about 100 years ago. So our ancestors and all of the animal ancestors before them basically had these rods which are designed to help us see in periods of situations of low light. But in the modern world in which we live, where it's lit most of the time, even at night, our rods are completely maxed out. So they're screaming all the time, providing very much little information. Your rods in your head right now and your eyes are probably just going, ah, like that, and not giving you much useful information. So let's forget about them for the rest of this talk. Basically, what happens is you've got cones, and they are the red ones. They're called red and green and blue by biologists, but that's actually sort of misleading because the red sensors are sensitive over almost the entire range of what we call visible light. The green ones are also sensitive over almost the entire range, but not as sensitive to light overall as the red ones. And the blue ones are hardly sensitive to light at all for those people who have blue ones. Some people have defective ones. And so the human visual system does not work the way a camera works. The camera visual system essentially works by addition, right? It takes every pixel is the sum of the red, green, and blue response to the light that is hitting that pixel. That's the RGB value that you're familiar with. The human visual system can't work that way because how could it work that way if the sensitivity ranges of the three kinds of cones overlap so much? It could not work by addition, so it doesn't. It works by subtraction. Okay, so there are basically three channels of information coming from your cones to your head. One of them is yellow minus green, or it's green minus yellow, I can't remember exactly which. And the other one is blue minus, sorry, did I say red minus green? One's red minus green, and the other one's blue minus yellow. And then there's a third one, which is a complicated function of additions and subtractions that produces brightness from the cones. So the cones are producing the brightness information as well as the color information, and they are doing it by subtraction, not addition, which makes our visual system almost insensitive to absolute brightness levels. So if I take this illustration, which a college classmate of mine, Edward Adelson, produced, and you see the checkerboard. Can you see the square? There are certain squares in the checkerboard marked A and B. Can you see that? What if I were to tell you that the A square is the same shade of gray as the B square? It's the same shade. Okay, so I'll demonstrate that to you by taking a piece out of each one with Photoshop and putting it over there on the right. Okay, now but you still don't believe me. You think I cheated. So I'll take the image, blow it up, and then I'll cover up that piece, that piece, that piece, that piece, that piece, and that piece. So the human eye is really not designed for detecting absolute brightness levels. It's designed for detecting differences, edges, changes. That's what it's designed for. So what that means is that humans have trouble discriminating certain kinds of color pairs. So for example, if two colors are both pale, people may not be able to see the difference between them depending on exactly how their rods and their cones function. And also, by the way, on the kind of display that they're looking at. Like, for example, I'm looking at this on my Macintosh screen, and you're looking at it on a projected display. And then there's also these monitors here. And all of those can influence how you see the two colors and whether you can tell the difference between them. So all you color designers out there, your graphic designers who think that you're in total control of the color that your users are seeing, forget it. You are not in control. Their eyes are in control, and the displays that they're using are in control. Similarly, people have trouble discriminating color patches that are small. So if you have two color patches that are very small, and the colors are close to each other, people aren't going to be able to tell the difference. But if you make those same color patches larger, it'll be easier for people to tell the difference between those two colors, right? So what does that say if you're making a graph and you're putting the legend over on the right or underneath the graph with little dots that show you the different colors of the different lines? Make those legend dots big. Don't make them little tiny squares, because people won't be able to see the difference between them. Color perception is, comparing colors is also easier when the patches are together than when they're separated, especially if eye movement is involved. Because if eye movement is involved in the comparison, then memory is involved in the comparison. So if I move these two together, it's easier to tell that they're different than if they're separated. So if we look at itn.net, which is a website for ordering airplane tickets and hotel reservations, and we see that they have said that they're showing me what step of their process they're on. And they're trying to show me that they're on step 1. But they're using pale yellow to mark the steps. So we're on step 1 now we're on step 2. Can you see that change? Some of you can probably see it and some of you probably can't. And it also will depend on the display that you're using. Some people have color blindness. So about 8% of males and about 0.5% of females have some kind of color vision deficiency. Now, color blindness does not mean people can't see colors. It's sort of the term color blindness is misleading. What color blindness means is that there are certain pairs of colors that people cannot tell apart. So for example, a friend of mine who's red-green colorblind cannot tell the difference between these two lines. To him, they look the same. Okay? Now, just out of curiosity, is there anyone in this room for whom these two lines look the same? We're looking for the 8% number here. Okay, yeah, so there's one. Okay. So now think about that. Think about that for a second. If you create a graph in which different, let's say it's stock values over time, and Apple, Google, and various other stocks. So, and the lines cross. It's not just that the person is not going to be able to tell which one is which. Wherever they cross, they won't even know which one goes on from that point, right? So it's a really serious issue for people who are colorblind. So you really have to be careful. My friend who is colorblind also can't tell the difference between these two lines. Now, he's classified as red-green colorblind, but this line one of them I would call blue, and the other one I would call purple. But he still can't tell the difference between these two lines, okay? And this one, one is black or dark brown, and the other one is red, or, yeah. So he can't tell the difference between either of these two pairs. So you really have to be careful. No, I don't want you to go out of this room and say, Jeff Johnson says don't use color in our user interfaces, because that would be pretty boring. What I'm saying is don't rely solely on color to convey information. If you're conveying information with color, use other cues that are redundant with that. So for example, I would improve itn.net's display by in addition to using a brighter, more saturated yellow to mark the current step, I would also bold the box and the word and the number. Now, how they improved it without actually asking me, they never consulted with me, unfortunately, but that's fine. They improved it this way, by making the step sort of inverting its color and putting the sort of blue area around it. Now, that's just as good. So basically, people are going to be able to regardless of what their color vision problem is, or what kind of monitor they're using, they're going to be able to tell what step they're on. Now, peripheral vision. Human peripheral vision is very bad. It's very poor. There's an error message on the screen. Does everyone see it? It's right there. This is an actual screen of a login screen of a web app that a client company of mine created. This is an actual screen, okay? And that's where the error messages were displayed. And so in usability testing, here's what we saw. User types in ID. They type in PIN number. And in some cases, we gave them incorrect IDs and PIN numbers so that they would get an error message. Okay? And what happens is the user types the ID, the PIN number, and they hit login. And the screen redisplays, and the fields are blank. And the user goes, what? What? Why did the screen redisplay? Why are the fields blank? I don't get it. I must have hit cancel. So they fill in the ID again, which is still wrong, and the PIN number, or one of the two is wrong, and the screen redisplays again. And they go, huh? Am I nuts? That time I was paying attention. That time I know I hit the login button. What is going on here? Oh, why didn't I see that error message before? Here's why. There are actually 3 reasons why they didn't see that error message before, and they all combine to make peripheral vision of humans and actually almost all mammals horrible. Reason number 1 is that what we're seeing now on this graph is the distribution of rods and cones across the retina. So in the center, now as I said earlier, we can pretty much forget about the rods, but you can see that there's none in the middle, there's no rods in the middle, and then they shortly, a little bit away from the middle, they're pretty dense, and then the density falls off as you get to the periphery. And cones, on the other hand, are very dense in the middle. That is to say, there are 158,000 cone cells per square millimeter in your fovea, in the center of your visual field. Now, to give you an idea how big that visual field is, I want everyone to hold their arm out at arm's length and hold your thumb up. And look at your thumbnail. Look directly at your thumbnail. Your thumbnail spans the size of your fovea on your retina. And the rest is periphery. Everything else is periphery. So your thumbnail is 1%. You know, we've heard a lot recently in the news about the 99% and the 1%. Here's another one. The 1% of your visual field in the middle, when you're looking directly at something, the 1% is the fovea. And that's high res. Everything else is low res. Everything else is low res. So, and there are 3 reasons why everything else is low res. And reason 1 is the density of the cone cells in the middle is 158,000 per square millimeter. And in the periphery, not very far from the center, it falls off to 9,000 per square millimeter. Now 9,000 is a lot per square millimeter, but it's not 158,000. Okay? Does that make sense? That's reason 1. High density pixels in the middle, low density pixels everywhere else. The other reason is that in your retina, every cone cell in the fovea sends a fiber out to the optic nerve that goes back to your visual cortex. Every nerve cell in the fovea sends one fiber. The optic nerve that leaves your eye and goes back to your visual cortex is a cable with millions of fibers in it. Every cell in the middle of your visual field, in that middle 1%, sends a fiber out. In the periphery, which is everything else, in the other 99% of your retina, 3 or 4 cone cells combine to send 1 fiber. So what does that mean in computer geek speak? It means that data coming from the middle is uncompressed, and it's compressed with data loss everywhere else. So you can think of it as you got a TIFF in that middle 1%, high res, and you got a JPEG everywhere else, low res JPEG. And reason number 3 is that when you get back to the visual cortex at the back of the brain, which is called the occipital cortex, There's a map. The occipital cortex forms a map of the retina, but half of that map is devoted to processing from the 1% fovea area, and the other half is for the rest. So think of it that way. Your brain, your eyes, by the way, biologists consider your eyes to be part of your brain. But anyway, your visual system is set up unlike a camera in almost every way, because a camera has its pixels distributed evenly across its plate. The human eye has high resolution in the middle and low resolution almost everywhere else. So let me tell you, the resolution of the human eye at the fovea is approximately 300 dots per inch at arm's length. If I print something on your thumbnail at 300 dots per inch, if you have normal vision, you can see the dots. What is the resolution of your visual field at the edge? Guesses. How many dots per inch? It's measured in dots per foot. The answer is 3. The effective size of a pixel at the edge of your visual field is approximately the size of a cabbage at arm's length. Now everyone's rolling their eyes and looking around the room and saying, I see everything in high res. Your eyes move 3 times a second. You can't control it. It takes 1/10 of a second for an eye movement. By the way, your vision shuts off during those saccadic eye movements, but you don't see the world in blinks. Here's an interesting exercise you can do later, which is stand in front of a mirror, put your face right on the mirror, and look at your left eye, then look at your right eye, then look at your left eye, then look at your right eye. You will never see your eyes move. But somebody standing there watching you will see your eyes move back and forth, but you will not. What you will see is you're looking at your left eye, you're looking at your right eye with no time in the middle. That's because during saccadic eye movements, the brain shuts down, but it also takes those 2 pieces of video and it stitches them together in time. So you never notice the little black intervals. Okay. So if we look at this website of airborne.com, this login page, we notice one of the things we see is that there's an error message here in red over on the upper left underneath the title. But it turns out people also have trouble seeing that error message because they've pressed the login button. Well, now we know why. Because if we show what the eye sees when a person has clicked the login button before they move their eye at all, before the eye moves, this is what they see. This is what the eye sees at the moment the login button is clicked, before the eye moves anywhere else. And remember, eye movement is somewhat random. It is actually guided by goals and many other things, but one of the things that can make it move somewhere is movement or change. And the problem is there was some red stuff in the upper left before, and now there's still some red stuff. So the eye doesn't really see a change. So there's no reason for the eye to actually move to the upper left. Therefore, it's not going to see that error message. Or at least there's a probability that the eye will not see that error message. I think that the probability that the eye will see this error message is higher than it was in that previous one, but it's still not guaranteed. And of course, this is why you get in usability tests, programmers in the back room watching the usability test and saying, what's wrong with you? Don't you see it? It's right there on the screen. No, because they're human. They don't see it. Because their eye was not given a reason to move in that direction. So in terms of user interface design, how do you make sure error messages can be seen or information can be seen? Well, put it where users are looking if you can predict that. Put it near the error. If there's an error, use red for errors, or use an error symbol, like one of these error symbols. Now, here's an example of that. So for example, at AOL.com, if you sign up basically for their service, there's a long form. I haven't shown you the whole form. You go down and fill out all the stuff on the form, and then you click done. And if you've got a password that they don't like for some reason, they will send you back, they'll scroll you back to this place on the page. They put an error symbol there. They tell you how good your password was. They put an error message, which is in red. They highlight the field you're in, and they put the cursor there. You're not going to miss that. Now, there is some heavy artillery that you can use to make sure people are going to see error messages or other kinds of information, but you have to use it carefully. You can pop up things in error dialog boxes in front of the user. You know, some people hate that. Other people turn off pop-ups in their browser. So there's certain situations in which that's not a useful thing to do. There's audio. You can beep. But of course, imagine a room like this where everyone's got their computer and they're all beeping. Whose is beeping? I can't tell. So audio is limited. Then there's flashing or wiggling briefly, but not continuously. If you flash or wiggle constantly, some people get epileptic seizures, and other people will not look at it because they assume it's an ad. So for example, this is something you're going to see more and more of in the future, and you're starting to see more and more of in various places, which is if you want to get somebody's attention with an error message, you wiggle it. That error message went 1 pixel up, 1 pixel down, 1 pixel left, 1 pixel right, and it stopped. Stopping is very important. Okay? That will attract your eye. Why? Because it might be a leopard. Right? Your eye does not know what that is. It just knows that there's movement in the periphery. So it yanks the fovea right over there because it might be a leopard. Right? Yeah. So blinking is a poor substitution for wiggling if you can't wiggle, but it's better than nothing. But again, important thing is to stop. Okay, I'm going to talk about cognition now. I'm going to switch gears and talk about cognition. Short-term versus long-term memory. When I was in graduate school, cognitive psychologists believed there were places in the brain where there was short-term memory, and there were other places in the brain where there was long-term memory, and the different brain structures accounted for them, and they had models of short-term memory and models of long-term memory. That's not the view anymore. Now that people can actually study the brain in operation using magnetic resonance imagery, now we know that short-term and long-term memory are actually just two characteristics of the same memory system operating. And short-term memory is now much more closely tied and interpreted as being tied to perception and attention than it was in my graduate school days. So short-term memory is what we call, is now considered to be, it's a representation of your conscious mind. It's what you're attending to right now. So short-term memory is not a place. It's not a place where things go from perception and things are brought in, hauled in from long-term memory. It's not like an accumulator in a computer. That's not what short-term memory is. Short-term memory is the stuff. Oh, think of it this way. Your memory system is this huge warehouse. And everything in there is old and dusty and covered with cobwebs. And occasionally something new gets shoved in through the doors. And while it's being shoved in through the doors, it's illuminated because the door is open. And then the door slams shut and the stuff comes in and it goes dark just like everything else. Except that there are 4 searchlights in the ceiling. And they can look at 4 things at once. 4, not 7. How many of you remember the magical number 7 plus or minus 2 from your school days? That is now known to be an overestimate. The actual capacity for short-term memory, and when I say capacity, I don't mean it's a place, it's not a bucket, but you have 4 searchlights that can look at 4 things at the same time. Some people have 5, but most people it's 4. 4 plus or minus 1. For dogs, it's 1 plus or minus 1. And so those 4 things that those 4 searchlights can be looking at any time are things like goals, numbers, words, objects. And if a searchlight is pulled away from what it was looking at, then the old thing is lost from short-term memory. So short-term memory is, again, it's not a place. It is a It's what you're attending to right now. So that's why you can have the situation of sitting in your living room reading and then hearing the cat meow and saying, oh, I have to feed the cat, and getting up to go and feed the cat, and then having the phone ring and then having your brother talk to you on the phone. And then you finish talking to your brother on the phone, then you go sit down and you go back to reading. And then the cat meows again and you go, oh, I forgot to feed the cat. Because your brother's call pulled one of the searchlights off your goal of feeding the cat, okay? So here's a short-term memory test. Memorize those numbers. Say your phone number backwards. Say your phone number backwards. Go ahead. You do it? Okay, what were the numbers? Anyone know? Okay, memorize these numbers. Now, if you notice something about those numbers, namely that they're the first 7 digits of pi, it now is not 7 things to remember, it's 1 thing to remember. And your brain can do it much more easily. Memorize these numbers. That's probably 3 bits, right? It's like odd numbers starting at, ending at. Memorize those words. What are they? Not bad, not bad. Memorize those words. Same number of words. Same number of words, 1 chunk. So if we go to this website and we look at what it's showing us search results. So somebody has done a search and they're looking at the results. And here are the results down here. And the website is nice because it's showing us, it's giving us a way to fill in advanced search options if we want to adjust our search. But there's something important it's not showing us. What is that? What did we search for? And of course, I'm going to defend the programmer now, and I'm going to say, well, you only put it in 10 seconds ago. What's wrong with you? Can't you remember something for 10 seconds? No, because I am human. I have 4 searchlights in my brain. Maybe some of you are lucky and you have 5. But you got a certain number of searchlights. And they were totally pulled away from my search terms by the search results, because now all my attention is focused there, trying to figure out, are those results relevant to what I was looking for? Okay? Now, long-term memory is that warehouse I was talking about earlier. And the memories in there, memories are also tied to perception in the current view of cognitive psychologists. Think of it this way. If I look at his face, let's say I look at Dan's face, what happens in my visual system is, starting at the visual cortex and moving forward in my brain, millions of neurons fire, a huge pattern of neurons fire. And that pattern is my recognition of Dan's face. That's my memory of Dan's face. And if I look at Ben, a different set of neurons fire. It's very much similar because he's human and he's, they're about the same age, I guess. But they're not the same. And so I'm not going to, the thing is, the human brain can tell the difference between this pattern of 1 million neurons and that pattern of 1 million neurons firing. And if I run into Dan on the street in San Francisco, another set of neurons will fire. And it'll be very similar because he's the same guy. But it won't be the same because we're in San Francisco and not in this room. And remember how we learned earlier that context impacts perception. And so I might recognize Dan on the street in San Francisco, and I might not. Especially, let's say, if he shaved his beard. Or what if I run into Dan's twin brother on the streets of San Francisco, and I say, whoa, hi, Dan. And his brother goes, what are you, some kind of pervert? Get away from me, right? so what's happened so here's the important thing is that a huge pattern of neurons fires. That is recognition. That's what recognition is. And so experiences trigger patterns corresponding to features in your brain. Your brain is a feature recognition machine. That's what your brain is. And so similar experiences trigger the same pattern. That's recognition. Recall, in contrast to recognition, is something completely different. Imagine what recall is. Recall is a particular pattern in your brain of millions of neurons becoming activated in the absence of the stimulus that produced it in the first place. That's hard. Your brain is actually not designed for that. It's designed for recognition. Okay? Getting a particular pattern of neurons to fire again, evoking a memory in the absence of the stimulus that originally produced it, is difficult. That's why recognition is easy and recall is hard. And that's also why the fact that these patterns are big collections of features is why the memory, long-term memory, is error-prone, impressionist, free associative, and easily biased. So for example, features may get dropped from a particular memory. So you may have seen a whale shark when you were out on a trip, and 20 years from now, you and your brother argue about whether you saw a whale or a shark, because features got dropped from that memory. So here's a long-term memory test. Was there a roll of tape in the toolbox? Good, good, good. What was your last phone number? The one before you have now. Does anyone remember it? You do? Oh, that's good. Was this a Pollock painting or a Dalmatian? You'll never, ever see the Pollock painting in this again. So you shouldn't be burdening long-term memory as a designer. So for example, here's an instruction that a designer gave to a user, which is kind of funny because the designer knew that they were asking the user to do something that the user can't do. Change your PIN to a number that's easy to remember. That's part one. Part two, a PIN can be 6 to 10 digits and cannot start with 0. Your PIN must be numeric. They've just given you instructions that you cannot follow. And they know it, because at the bottom it says, remember, please write down your PIN. Put it on a yellow sticky underneath your computer so that any guy can come in and steal it. Having your brain keep track of features, keeping those searchlights trained on certain objects in your memory is work. It actually takes calories. And so your brain does it as little as possible. So your brain tracks only features crucial to the task. So that causes something called change blindness. So if I show you this picture, and then I change it, I want you to tell me if there's any change, or what has changed. What changed? Okay, let me change it in a different way so that I remove the pause in between. Okay, so your brain is going to focus on the people, because you're human. Your brain will focus on the people and their food and the beer, probably. Okay, and so people say things like, well, he had a mustache in the first one, he didn't have a mustache in the second one, or something like that. But no, it's things that are irrelevant to what you're interested in that you aren't going to notice. So I'm getting close to the end. I'm like 2 slides from the end. So as I said earlier, recognition is easy, recall is hard. We recognize things extremely quickly. It doesn't take you very long, especially if you're out in the wilderness, to notice something like that. Okay? Because otherwise you wouldn't be passing your jeans on. Right? I took this picture, by the way. Talk about getting into the vehicle quickly. So Lucy, walking around on the African savannah 4 million years ago, had to be able to recognize objects very quickly, otherwise we wouldn't be here. It doesn't take you very long to recognize this face, these faces. And even more tellingly, it doesn't take you very long to recognize that you don't recognize these faces. And what this shows is that when I was in graduate school, people thought of the brain as a computer, and they were trying to figure out what are the algorithms that the brain uses to do face recognition. And so then they said back in those days, well, it can't be, is it this one? No. Is it this one? No. Is it this one? No. It can't be that because it's way too fast. So they said it has to be something like, is it in this half of the database or in this half of the database? It's in this half, okay? Take it and split that in two. Is it in this half of that half of the database, in this binary search? And no, it's way too fast for that. Face recognition is way too fast for that. So they came up with all these algorithms back when I was in graduate school about how the face recognition can be so fast. And now we know why it's so fast. It's because the brain does not search. The brain is a content addressable, holographic memory device. It's a recognition machine, okay? Like I said, those big patterns go off. So it's basically face recognition and also recognition that you don't recognize a face is almost instantaneous. It's not searching. There is no search. Similarly, people can recognize, very sophisticated patterns, like, for example, Kasparov versus Karpov, 1986. If you're a chess master, you'll recognize that. If you're not, you won't. Finally, I guess I'll talk about performing learned routines versus new behaviors. Performing learned routines is easy, like riding a bicycle after months of practice, driving to the same workplace after many years, and using a touchpad after a few years of practice. Now, the reason that's easy is that it's automatic. Cognitive psychologists make a distinction between what are called automatic processing and controlled processing. Automatic processing uses lots of different parts of your brain. It doesn't use up short-term memory, so it's not using up those 4 searchlights. It's what computer scientists would call compiled mode or parallel processing. There are many processors. You can multitask automatic things, okay? So one way I think of it is that every part of the brain is a brain. And so things that are automatic and running in compiled mode, essentially, you can do many of them at the same time. That's why I can walk and chew gum at the same time, or I can be whistling a tune that I'm very familiar with. But try to do that with something new. Following a new cooking recipe, driving somewhere you've never been, writing with your non-dominant hand, switching from Mac to Windows PC or vice versa. That's controlled. That consumes short-term memory and attention. It's what we computer scientists would call interpreted mode or serial processing. There's only one processor there. It's called the attention. There's only one processor and you cannot multitask. So you can only do one novel thing at a time. You can multitask a novel thing with automatic things, any number of them. So let's just do a test and recite the alphabet, A to M. Go ahead. Recite the alphabet, A to M. Easy. Recite the backwards, M to A. That's controlled. Requires short-term memory. Requires attention. Hum the first measure of Twinkle, Twinkle, Little Star. Go ahead, do it. Hum it backwards. Controlled processing. Requires short-term memory. Requires attention, full attention. So all of the things that I've showed you is why user interface design is a skill, not something anyone can do by following user interface guidelines. And that's why knowing the cognitive basis helps us prioritize and recognize which rules to follow in each situation. Now I'll take any questions that anyone has for as long as you want. Thanks. Yes?
So this model of short and long-term memory that you were discussing, how is this consistent with the fact that there's a phenomenon where people who, for example, go unconscious in accidents or concussions lose all memory of the 4 or 5 minutes preceding the accident? People who take Versed and not lay down memories while they're under the influence of the drug. So how that model seemed, or those results seem to match the old model of there being a different short-term memory from the long-term memory.
Yeah, I mean, one of the things that had been noticed when I was in graduate school was, people come back from combat situations with certain parts of their brain shot away, or auto accidents or whatever. Some of them can remember new things and others can't. And other phenomena like the ones that you described. And so that's why they sort of thought there had to be these certain places where there was short-term memory and other places that was long-term memory. And what they now know, or now believe, is that there are certain areas of the brain that are essentially gateways. They're sort of, bottlenecks for information. And if those are shot away or just damaged, then the ability for the brain to sort of generate and compare these patterns becomes destroyed. So that's basically it. It's now thought of as, instead of that short-term memory is here, let's say in the hippocampus, because that's where they used to think it was when I was in graduate school, is that the hippocampus is somehow, well, remember I said earlier the human brain can compare patterns and can tell whether it's seen a pattern before? They don't know why that is, but maybe it's possible that the hippocampus is involved in that, in that comparison. So, I guess what I'm saying is that now the understanding of short-term memory versus long-term memory is not as cut and dry as it was back in the 70s, when they thought that, short-term memory is in the hippocampus and long-term memory is in the cerebral cortex or something like that. I don't know if that answers your question.
Well, it doesn't explain those phenomena, but maybe I have to look deeper for that. I understand.
Okay, so say again what the phenomena was.
The phenomena that someone in a car accident does not remember 3 minutes before the car accident.
Right.
Which normally would have been laid down in, short-term memory or long-term memory, whatever you want to call it.
Right. And so there is some process by which stuff comes in from perception and gets put into long-term memory. I mean, one of the things that we know now, which is kind of interesting, if you're a musician, they know now that it's better to practice for 15 minutes and then sleep, and then to practice for 8 hours, because the sleep has something to do with the stuff that you practice getting laid down. So I don't know if I can answer your question fully.
About peripheral vision, sometimes people talk about athletes, they play quarterbacks, having great peripheral vision. Has that been tested? Do some people really have better peripheral vision?
Well, I wouldn't doubt it, since there's all sorts of genetic variation and there's a lot of randomness in our genes. And so that's why, for example, those people 4 million years ago who could actually see the leopard coming at them are the ones that survived, and those who didn't see the leopard, maybe the Neanderthals, are not. Okay? Not that I know of, but one thing that, have you ever heard of the Door study? If you go to YouTube and type in the Door study, okay? So that's a situation where it's not really peripheral vision, it's more has to do with change blindness. But basically, if you get someone in a situation where you change out a person in front of them, they're interacting with a person and you change the person out. Oh, yeah. And a lot of people don't notice, but some people do. And so and they don't know yet whether there's any systematicness to that or whether it's just random.
I was wondering, do you recommend can some user interfaces or touch and interactions rely more on long-term memory, and others have to be designed for a situation where someone has to keep track of everything right then?
Well,
how do we apply this in that way?
I mean, okay, so it's certainly the case that some user interfaces are designed to be walk up and use, or at least to be used in a situation where it's been a year since you walked up and used it before. And so you're not going to remember details. Like, for example, recovering files from a backup system. How often are you going to have to do that? Okay? So that user interface is probably going to have to be designed differently from the user interface for handling your email, which you do every morning for half an hour or an hour. You know? So, and you know, people who design walk up and use interfaces really have a different sort of mindset, a design mindset, than the people who are designing user interfaces that are going to be used by people who have a lot of experience in training. I'm not sure that exactly gets on your question, which was?
Yeah, I mean, I think that ties into it.
Yeah, I mean, yeah, the thing is, some air traffic control, for example, intense information overload all the time, you know, and also extreme danger if you screw up, right? So, so that user interface has to really support making sure that you can see things. So peripheral vision, for example, if there are planes over here, but you're looking over here, you need to, you know, they need to do things, you know, they have to somehow get your attention. Actually, a lot of people these days are thinking about user interfaces for security guards at airports and things like, and places like that, security checkpoints. Because think about that job. Nothing happens for months or even years at a time, and then something happens, and you have to be attentive, right? But it's hard to be attentive when you've been bored for 3 years. So how do you design a user interface to make sure that someone notices something is happening now when nothing has happened for the last 3 years? You know, so there's a lot of attention being paid to that particular problem. Okay, thank you.